guys see that I posted the recorded video on the course website for our last lectures on this class. So I posted that recorded. Yes, you saw that, right? Okay, yeah, that should help. And today I'm going to record as well in case some of you miss. You don't have to open the computer, some of you will not have access. So you just watch how I do that. All right, so I'm going to today I am going to show you how to create body diagram of first order low pass filter. So for that, let's revisit the first order low pass filter circuit. So I'm just going to create a new page. See, the first order low pass filter circuit looks like this. So this is R, and we have a capacitor. You take the output from these two terminals and input. You have sinusoidal inputs. You have sinusoidal inputs. So this input was summation of three sinusoidal components. Let's say overall, I'm just going to put the VI, VIT, and the transfer function is basically of this low pass filter is H of M is simply V out in frequency domain, function of frequency, and input as a function of frequency. Now, in OrCAD PSpice, we have voltage marker, current marker, power marker. So we can actually measure the voltage. We can see the voltage. But this is basically a ratio of two voltage components. So it's unitless quantity. So for that, what I'm going to do in sinusoidal input, there is a parameter for AC. So what I'm going to do, I'm just going to put out of M, V naught of M over 1. So AC component, I'm just going to AC parameter, I'm just going to put 1. So that we see the magnitude of this output is same as this frequency response, H of M. So we are going to put voltage marker here, that is going to show the magnitude of this frequency response, H of M. And again, this is an unitless quantity, but we will use a voltage marker to get this frequency response. Let's get started. So you start OrCAD PSpice. dielectric. So it is going to be dielectric. And let's say R2 A was bigger, and then I'm going to call it body. Create a blank project. Okay. So here, I'm going to this parts. So see the top. Here R. And capacitor C. Let's look at this capacitor. So that terminal 1 is on top, terminal 2 is at the bottom, and then I need the sign. So now I need ground as well. Ground. Okay, I simply connect. Okay, so here the resistance I just made R, and then how much was the resistance, guys? 159. For example, and then I'm just going to move this label like that. C, and then it was 10 microfarad. 10 microfarad. So total market here is price, markers, motor market. Just want to put it right here. Okay, here, you just have to give parameters here, otherwise it's going to give you the error, offset 0. Amplitude, there are 3 components, but any of the components, you take any of the components, because these would not be taken into consideration, because we would be running the simulation, which is going to be magnitude with respect to frequency, magnitude versus frequency. So amplitude just put 5. The frequency, let's say 10. Again, we will have a frequency. So x-axis is going to be frequency. But what is important here is the we just put 1. Just put 1 here, so that this voltage marker becomes the frequency response. Rate of it. Save. Now create simulation profile. Give a name. So RC underscore LPF local splitter body. Just for the sake of for convenience, I'm just going to give the same thing. Because the data extension is going to be different, but it does not be the same thing. So I create a simulation profile. Here, instead of time domain, I'm just going to choose SEC. And then SEC type linear logarithmic. I'm just going to put logarithmic scale. X-axis is going to be frequency in logarithmic scale. And start frequency, I'm just going to put 1. And end frequency up to, let's say 1 megahertz. 1 megahertz is 6, 1 up to 6, 0, 10 to the 6. So 3, 4, 5, 6. And points per decade. So per decade, let's say I want resolution like 1000, that is enough resolution. So click OK. Now simply run PSpice, run simulation. So we should see the output window in a moment. Okay, there. But you see, y-axis is in volt. Okay. But you can actually show the y-axis in decibel. Actually, you don't see. So what you do, you change the width of this line. So trace property, and then those colors blue with make it a little bit thick. Okay. Now, to show this y-axis in dB, what you could do, you can double click here. So it is going to be voltage across capacitor from terminal 1 with respect to ground. So you see the mathematical functions, you see here dB. So what you can do here, you can simply write dB, and then between parentheses you pass this voltage as an argument. So click OK. So this is going to be in decibel. This is in decibel. So the break frequency is 1 over 2 pi RC was the break frequency. If you substitute the values of resistance and capacitance, you will see the break frequency is 100, about 100 hertz. So at break frequency, you see this difference is about D. So it makes sense. All right. So that's all I'm expecting you guys. Okay. So I'm going to stop the recording right here. Now it's going to save my desk. I'm just going to post this recording on yes. This one? Okay, so here, all what you do.
This.
Simulation profile?
Yes.
So what you do, what I did, even from here simulation, so edit profile.
I'm home.
Oh, okay, okay. Okay. The schematic window. Okay. All right. Actually, I'm sorry, yes, I need to get my chargers because of the recording. I'm hungry. So I'll be back from my office.
gives us something. Hopefully it's just like adding them like they do all over.
Right.
Because I could just use the calculator. It's supposed to just be
He does this, bro.
check that out.
It's pretty much what I got too. Shit, yeah.
I didn't even really need this one.
I'm just, dude, I'm crazy on a tweet.
Yeah,
Strike me crazy.
No, honestly, I don't think much formulation would help you with this.
Because on the last lecture, he just skimmed through this shit. He just fucking don't fucking.
Yeah, I mean, it's first time he gets class too. Myself for
I think he
but
might
also
be
that self.
he's gonna be too smart for us.
Well, he wouldn't fall through all of it.
So it's one of those things, dude. Like, it's cool, dude. Like, even Coach other said so himself. It's like, it's cool seeing all this shit play out in theory and, you know, all this shit, but like, it doesn't really click until you do it. You know?
Yeah.
Like, how do I apply this to an actual strike?
You have to actually do
I guess doing this whole simulation thing helps, but I mean, are we doing this right now? Like, for actual class? No.
I mean, we can do that.
It'd be cool to do these examples on the thing. I guess we could, though. I guess I'm just stopping this. We have time.
Who? I think he was dragging raw, so I could have done him entire maybe.
Any questions, guys?
I'm taking this as like it's what he's at. I'm just gonna like try and do my best and then see what kind of quizzes
We
he
can do it after the
gives.
class. I will post
Right
this
next time.
video on my course website. Let's get started with our module 2. So operational amplifiers. So in this chapter, we are going to deal with circuit, actually one block. Operational amplifier is the most fundamental function, most important function. So what it does, it actually amplifies the signal. That's why it's called amplifier. Okay, it amplifies the signal. And the reason it is called operational is because it can do some mathematical operations. For example, summation, subtraction, differentiation, integration. All these mathematical operations, this operational amplifier can perform. In this chapter, we will study the operational amplifier as a black box. We do not know what's inside. We will learn. We will learn how these operational amplifiers create. Okay, we will learn that. But in this chapter, we are going to study these operational amplifiers as a black box. We do not know what's inside, but we do know its functions. So op-amp. In short, I'm going to call it op-amp. So we'll have input signal, VIT, and we'll see output signal. Output signal, Vout, T. And the gain of this operational amplifier, the gain, we would be mainly talking about voltage gain. So voltage gain, AB, is going to be Vout of T over Vi of T. Okay? So we will be mainly talking about the gain, the multiplying factor. So the output is going to be input multiplied by this scaling factor. Ideal op-amp. Here I gave some introduction here. op amp, we will just create this as a black box. But in real life, actually for your first laboratory assignment, you will be using op amp as an IC. You know, op amp looks like this IC. There are eight pins of this op amp. This is op amp. So 8 pins. So you do not know, we do not know what's inside, but we will be looking at the operating principle of this op amp. And the op amp that you will be using in the lab, in your first lab, is this one. LM6482. LM6482. So yeah, your op amp will look like this, and this is the data sheet. I'm going to post this data sheet on the course website as well. This is the data sheet, and we will learn all the parameters, how to read this data sheet. Okay, and for simulation, you may want to just write down which library you are going to use. For simulation, you need to add one library. I have added this library as well. Library is called op amp. And how to add this library for the simulation, how to add this library, you simply click add, and then this is also written in the PSpice Quick Start Guide. I have posted that. Have you opened that file? So if you go to our course website, and do you see laboratory materials? ECE 303 PSpice Quick Start. Make sure you read this. And here I did mention how to where to go for adding library. So it is going to be tools, capture, library, PSpice. Now how to get to tools, because different people can install different configure. It's install, in different computer we have PSpice. Maybe the person who installs, he or she can install in different directories. So in our case, you will find the installation directory. It is going to be, so you go to PC and then C drive, C Cadence. It is under from this PC, C drive, Cadence in our computer, in our laboratory computer, we are installed here. So Cadence, you go to Cadence, and then you click on SPB 23, it's the version 23.1. Here you see tools. This is what I mentioned. So you see tools, and then capture, then library, then PSpice. Here you would see op amp somewhere. Do you see op amp? Yeah. So you just click that and open. So if you do that, then you should see this op amp right here. Once you click here, you will see all these op amp models. So here, in OrCAD PSpice, the op amp model that you would be using, it is called LM. Actually, mu A 741. 741, it's quite basic op-amp. I did use this op-amp when I was an undergrad student back in 2003 or 2002. So this is the op-amp you'll be using, but we do not have the op-amp that we have. We do not have the op-amp IC that you'll be using physically in the lab. So it is LM 6482. No, we do not have this model, but we have this IC. This IC is the better version, actually improved version of 741. But for simulation purpose, we will be using 741 mu 741 IC, which is the operational amplifier. Okay, but for practical implementation of the circuit, you'll be using 6482. Okay, we have this in the laboratory. The circuit symbol for this op-amp is as such. So we have these three terminals, terminal 1, terminal 2, terminal 3. And terminal 1, pin 1 is called inverting input, terminal 2 is called non-inverting input, and terminal 3, pin 3 is the output. So we provide input to this side, and the output is going to be in this side. Again, inside this op-amp, you will see there are many electronic components. You will see about 30 BJTs, 30 transistors, bipolar junction transistors, about 10 resistors, several capacitors, which are manufactured by the company in a single IC chip, a single crystal, in a single piece of silicon crystal. We call it an IC, integrated circuit. So again, in this chapter, we will be treating this as a black box, and we will know its function. We want to know how to use this for making bigger circuit. Now, one thing is because this is an amplifier, okay? This is amplifier, which means that it amplifies the input signal, right? You give 1 volt as an input, and you get 5 volt as an output, depending on the gain, okay? How does it get the extra power? Where does it get the extra power from? So what you have to do is you have to put some external DC power supply. So this op-amp that you will be using, you have to provide two DC power supply. One is called VCC, the other one is called negative VE. This is the negative supply, this is the positive supply. So if you draw the circuit diagram, so they would look like this. But for the sake of simplicity, a circuit would look very messy. So what we do not draw these voltage sources as such. We just use this notation. So where we will be using two voltage sources to power this operational amplifier, so that we get the output, which is multiplied, which gives the output, which is multiplication of input times the gain. And that gain, again, the gain is going to be dependent on the internal circuit, and the maximum output that you can get is VCC, and minimum output that you can get is negative VE. So I'm not going to read this text, you can just read at home. So I'm just going to explain the function. Now we are diving deep into different parts of this op-amp. This op-amp, the output, you get this output actually is multiplied by this gain, this is called open loop gain. This is called open loop. Okay. So the output is going to be open loop gain multiplied by this differential input. Which is nothing but the difference between the input to terminal 1 inverting terminal, actually input to the non-inverting terminal Vi2 minus input to the inverting terminal Vi1. Here, ideally, in this op-amp, the input impedance, ideally, input impedance is C in usually infinity. Usually infinity, very, very high input impedance. Because it has very, very high input impedance, current flowing through this terminal is going to be 0, and current flowing through this terminal is going to be 0. And the output V out is A times V2 minus V1. So this input, this differential input, positive, negative. This differential input is basically, V2 minus V1 is simply V out over A. So this differential input is basically V out over A. Now, ideally this op-amp has this open loop gain A. Ideally, this open loop gain is infinity. Ideally, this open loop gain is infinity. So if this open loop gain is infinity, then something over infinity is what? 0, right? Something over infinity is 0. So therefore, you can think of these two terminals as a piece of wire, virtually short. You can think of these two terminals connected with a piece of wire. Even though they are not physically connected, but you can think of these two terminals as a piece of wire. Because ideally this open loop gain is infinity. So this is what we have to keep in mind all the time. Current flowing through the inverting terminal here, it's going to be 0. Non-inverting terminal is going to be 0. And these 2 points are virtually connected to 0 voltage. There is no voltage. And impedance between these 2 terminals is infinity. So these are the parameters that we have to know. Ideal op-amp, that's how it works. These are the parameters that takes into account for an ideal op-amp, ideal op-amp to operate. I actually summarized these characteristics. Input impedance Zin is infinity, therefore, which implies that the current flowing through the input, inverting input terminal is 0. Current flowing through the output, current flowing through the non-inverting input terminal is 0. Infinite open loop gain, 0 output impedance, which means that whatever voltage you see, you can use this voltage as a voltage source. So that the output impedance, if you look at impedance on this side, output impedance is 0. So you can get whatever output you get, it's a solid output. You can just use this output voltage as a new voltage source. The other thing is infinite bandwidth, which means that this gain, the gain that you have here, this gain is valid for all the input frequency, ideally, from 0 to, I don't know, infinite frequency. Ideally, you can actually operate this operational amplifier with infinite frequency, 0 to infinite frequency. Therefore, the bandwidth is infinite. Zero common mode gain, so infinite CMRR. Output response only to the differential input, not the common mode signal. And you will see common mode and differential signals in a moment. Actually, I'm going to go through this in our next class because it will be 25 minutes for the quiz. So I'm going to distribute the quiz now. And we will start this class in our next class.
Yeah, YouTube again.